Good afternoon, all of you. So let us start our discussion for today. It is decision tree classifier that we are going to discuss today first, and then we will be talking about the data visualization for classification. So in the agenda for discussion, we have decision tree classifier, as I told you, and then data visualization for classification. We will be discussing example data set. And we will talk about their attributes and instances, scatter plot as a way to visualize the data and its relationship with other attributes, parallel coordinate graphs, Pearson correlation, and some example code in Python. Okay, so we have this decision tree. It is a tree-like structure. Of course, the tree is a conceptual idea of representing certain things in a hierarchical way. So the decision tree takes as input an object or situation described by a set of attributes, and it returns a decision. So basically you have certain values which are representing certain specific features of one class. This class may be representing an object or a vehicle or a decision. So this decision is the predicted output value for the input. The input attributes can be discrete or continuous. So we have already seen that classification learning is about learning a discrete valued function, while the regression refers to the learning of a continuous function, where continuous function has certain real values which we need to predict. In the classification, we need to predict the label of the class. So a decision tree reaches its decision by performing a sequence of tests. What do? We represent each test as a node of a tree, and all non-leaf nodes lead to partial decisions and assist in moving towards the leaf node. And we will see how we are representing the decisions. What is it meant by traversing from the root node till the leaf node of the tree, and how we can get stuck in the decision tree, how we will make the size of the decision tree more efficient by making certain guided heuristics to design this or construct this decision tree. Leaf nodes are the decisions based on the properties satisfied at non-leaf nodes on the path from the root node. So one thing you must be clear about is that tree is the representation of how to arrange the data in memory. Of course, conceptually, but we always want our systems to be trained enough to be able to perform some learning tasks so as to make them enabled in decision making. Can you tell me about how much you know about this tree structure? Yeah. Can you tell me about the tree structure in data structure sense? Yes. Okay. Yeah. So binary search tree, AVL tree, all these are the trees. But how do you understand the tree structure? And what is it meant by a tree node? Yeah. What do you mean by very basic? How is it very basic a structure? Yeah. So nodes contain data. It also refers to the parent-child relationship, right? Yeah, you're coming to the point. It is about address. It is about allocating some space in the memory. If you have a tree structure, the nodes are coming dynamically to the tree. Tree is not considered to be a static structure. Tree does not have a fixed size. It can have any number of nodes, which is dynamic. It all depends on the set of rules that you're formulating in this, right? So the tree is a dynamic data structure. So where do you store such kind of dynamic data? In which logical segment of the memory? RAM. RAM is completely one set of memory, and this is divided in 4 different logical sections. Yeah, cache is not part of the RAM in the sense that we are describing here. We are describing 2 different segments, one which is called as heap, another which is called as call stack. Cache is the memory where you are bringing the frequently used data. So it can be brought from heap, it can be brought from call stack as well. It depends on how you have programmed your operating system or how your programming operating system environment is supporting you. So there are 2 other sections in the memory. Which are those 2 other than heap and call stack? One is the area which is known as static area, where we place the assembly code which is participating directly in the execution, right? So all the program gets compiled by the compiler or gets translated into the assembly code by the interpreters and resides in the code segment, which is the static area. It has a fixed size. Code doesn't grow all of a sudden, so we keep it in the static area. And which is the other area? It is about the global data. So global data finds its place in static memory, which we get allocated through the static keyword in C language. So that way we have most of the compilers and operating systems working in collaboration to use efficiently the memory by dividing it into 4 segments: call stack, heap, data, global data, and code area. So when we talk about tree or any other dynamic data whose size is not fixed, we try to place that on the heap. Can you tell me how you allocate memory in heap using C language, if you have some idea? Yes, malloc is the right answer. Yeah, there are several other system calls, calloc, etc. They exist in C library, and you can allocate it on the heap area. So we are talking about tree where the nodes contain information about the test to be performed for taking that decision, and leaves which are only reachable through the branches of this tree one by one. As soon as the tests get qualified, we reach the tree leaf. So it is a hierarchical data. If we have opted for one branch, we do not go for the other branch. So definitely whatever decision tree is talking about, it is talking about some kind of memory which is allocated. It also talks about the efficiency of access to a leaf node, how quickly we can reach the leaf node so that our traversal time is reduced to the minimum. You have some idea about AVL tree. Can you tell me the difference between binary search tree and AVL tree? Yes, AVL tree is balanced. In what sense? Yeah, the difference in what? It is in the difference in height. So AVL tree is height balanced, and the height difference between the 2 sides is at most 1. So you can try working out with this example where you are trying to create all the time a balance, although it has some incurred cost. The reason is that whenever there is some skewed data as well, it is not going to create any disbalance in the tree, so that the search takes worst case order n time. That is why the effort in balancing and spending of time and memory in balancing. So the AVL tree's height is at most log n. So the worst case time complexity to search in the AVL tree is order log n. While the worst case time complexity of searching in binary search tree could be as worse as order n, because the tree could be skewed if I am giving you the ordered data. Suppose I am telling you 5, 6, 7, 8, 9, 10. In that order, if the data is appearing, then if you are building the binary search tree, it will be right skewed. Had it been the data like this 10, 9, 8, 7, 6, then the binary search tree would be left skewed, right? Left skewed, yeah. So you have sufficient idea of the tree data structure. You will now appreciate the usage of certain heuristics in constructing this decision tree, and we will also be discussing certain limitations of decision tree later. So now the effort is in constructing. There is some training set. You have already understood that there exists some data which is described by some features or attributes, and in totality they define certain class, right? So leaf nodes depict the decision about a character having attributes falling on the path from the root node. Each example that participates in the construction of the decision tree is called a training data, and the complete set of the training data is called training set. Yeah, the tree memorizes the observations, but it does not extract any pattern from the examples. So this is one very big limitation, that decision tree cannot handle unseen data, which is not the case with the neural network based classifiers. It is not even a case with KNN classifier. It just tries to find the minimum distance to one of the samples, and whichever is the nearest, the classification process gives the new unseen data also a label, which is possible for KNN. Also, it is possible for Bayesian classifier. It is possible for all neural network based classifiers to handle unseen data. But decision tree has a limitation that it cannot handle any unseen data, right? So testing data is possible, but it is possible only on the data which has been seen, so that all the tests your testing data has to pass. If it is almost similar or equally similar to one of the branches, that much prediction we can do. So it can be more helpful in some kind of routine task where you do not have much of the variations, right? So I'll give you some more examples later. So this limits the capability of the learning algorithm in that the observations do not extrapolate to the examples it has not seen. Okay, so how can we construct a decision tree for some face recognition problem? It is very difficult, of course, but let us talk about it. We define attributes. We collect the attribute data from training sample. We have, suppose, the images, then we will go for some kind of feature extraction. We may try to apply some image processing to extract the eye portion, or the distance between two eyes, or the forehead size, and so on. So many geometric features you could think of. Or we may go for some kind of more mathematical features such as wavelets, or discrete cosine transform, etc. But then once the attributes are collected, then we have to associate the output to it. Yeah, the question from Mayank, is decision tree a binary tree always? It is not necessarily true. The decision tree may be a n-ary tree. It could be having 5 children for one node and 3 children for another level of the node, right? So it all depends on how many values you can apply to the decision attribute. Okay, not necessarily the tree is balanced, but we try to see that there is some greedy heuristic applied to reduce the size of the tree. Yeah, so we will talk about it. Of course, it is not a balanced tree. We always go for a greedy approach, which may land up in some suboptimal solution, saying that the decision tree height could be very less, but not exactly minimum sometimes, because sometimes the greedy approach doesn't work as well. So we will see how we are going with that, and there is some information theoretic approach which we are using to reduce the size of the decision tree. So as long as face recognition class of problems is concerned, we may have to talk about thousand such attributes which are capable of discriminating between two persons, right? If there are only two persons or five persons in the database, then probably two or three or five concrete features, very prominent features, can distinguish between them. As all of us have in our family, we know a peculiar detail about each family member, and then it is quite easy for us to even recognize them when there is no power at home, or there is some different pose like that. But if you have a database of an organization where there are 500 employees working, then trying to discriminate between them through your machine learning software would require us to have at least 1,000 attributes. These could be some mathematical features as well. So it is very difficult to then go for decision tree type of classifier. This type of application is handled best by neural networks or support vector machines or different other kind of learning machines, but not through the decision tree because of its time complexity as well. So the attributes aid in taking the decision. The most appropriate attribute is selected for testing in the beginning, else the size of the tree becomes large, resulting in large computational time. So the most appropriate attribute is to be looked for, right? Leaf nodes represent the decisions. The attributes falling in the path from the root represent the attributes fully they are able to define the decision at leaf. Okay. Let us take this problem. In the last class, we had taken one problem of whether the person will be able to play tennis given the certain environment, whether it is a cloudy day or a sunny day, or it is raining, or it is breezy. Likewise, we can have a large number of other attributes for a different problem domain. It is an interesting problem where it is observed that there are certain attributes on which the values were collected, and it was obtained whether the person had to wait for a table at a restaurant or not. So the attributes defined like this: alternate, is there an alternate restaurant nearby? Bar, I mean, this is an example which is picked up from Artificial Intelligence book by Russell and Norwich. If you have access to that, you can go through that. Otherwise, this discussion is sufficient. So whether it is Friday today or Saturday, considering the fact that Saturday it will be more crowded and you may have to wait. Are we really hungry? So do we want to really eat and then go, and that is why we are waiting? So a lot of other parameters such as price, raining, reservation, type, weight estimate, etc. These are the attributes on which the data is collected, and it is observed whether the person has to wait or not, depending upon the complete pattern that is formed through these attribute values. Okay. Anirudh, which one? Which point did you not understand? Can you repeat? Okay. The attributes for, yeah, there is some typing error here. The attributes falling in the path from the root, they represent the attributes fully able to define the decision at leaf. So we will visualize this tree a little later with the example that we have. Whenever we have to identify based on the attribute values on one fine day, which is considered to be the test data, to understand whether we whether we will have to wait for the table or we will not be waiting. So such kind of decisions we will know only when we reach the leaf node from the root node. And on the way from root node till leaf node, you have to traverse all these intermediate nodes, which we call as non-leaf nodes, to be able to reach the next level of the tree. If any such test fails and you're not able to proceed further, it is not certain whether you will get any idea about whether to wait or whether not to wait. Is that okay? So, yeah, how does decision tree select root attribute? And when does decision tree terminate? It's a good question. We will be talking about how to select the decision tree root. It is about finding out the information content each attribute is holding. An attribute which has the maximum information content in it, which we call as entropy, will be the one which will be the deciding factor at the very first, right at the root, so that most of the decision is taken right there, and the subsequent branching does not require us much to test about. Yeah, so please wait, I will come to this entropy word. I was trying to answer the question about how to select the root attribute. So we will have that discussion about entropy. So this is a, let us say I make this kind of decision tree. Yeah, so I will come to your question, Yashasvi, a little later. So decision tree is made in some order. Probably I decided to use patterns, weight estimate, alternate, hungry, etc. as different nodes for testing. And whenever these are the red leaf nodes, they say that it is a F, right? And wherever this is a green leaf node, it is a true. So that means there you have to wait, and somewhere you do not have to wait. So the size of the decision tree depends on the choice of the attributes and the order in which they are used to test the example. So selection of attributes must be fairly good, yeah, and really useless attributes such as type should be avoided. You can always look at some of those details. Probably I'll come back to the same slide about the attributes. And you can always say that this is something which is not so important. Maybe the type, the kind of restaurant it is. Today you can see that everywhere there is a big crowd, big rush. So this may itself may be not the criteria for deciding whether I have to wait or not. Of course, if it is raining outside, the price range or several other things will happen, and we will see which one is the most important. Some of them will not be able to distinguish between the kind of classes we want them to. Okay. So let us come back here. So the quality of attribute can be measured. One measure can be the amount of information the attribute carries. Okay. It is not possible for us to end up in the non-leaf node because eventually the kind of observations we have all the data with us, and we have the decision also available with us. It is in the form of an observation completely for this feature vector and the decision class. It is basically a classification problem about decision making. So there is no possibility of ending up in the non-leaf node while you are constructing the tree. But once the tree is constructed, it is quite possible that for the testing data, you end up in some non-leaf node and you do not have sufficient information about that particular test data to proceed further. In that case, nothing can be said whether this class of decision or that class of decision would occur, right? So, is that okay, Yashasvi? So we may not end up in non-leaf nodes. So now we're talking about the information content. So if VI are different possible answers, right? So you can always see whether there are different answers possible or not. Say for alternate, is there an alternate available? Yes or no? This is a binary answer. Are we hungry or not? Yes or no? Um, Certain other things. Is it raining or not? Yes, no. But weight estimate, you want to find out, is it in this range, more than 1 hour, say half an hour to 1 hour, or within half an hour, or just 10 minutes. These are the 4 answers to us. So you can see that the node weight estimate has 4 children, right? So how many answers are possible? I can say for weight estimate, it is 4. For hungry, it is 2. For raining, it is 2. Patterns, it is 3, right? So decision tree necessarily not be a binary tree. It can be binary only if every attribute has only 2 answers possible. Okay. Yeah, whether to play or not can be implemented using decision tree or not. So the kind of information that I had displayed on that day is information which is not about the complete set of values. It is about the kind of number of instances that we had. So probability computation is possible through that representation of the example. Of course, I can always give you individual yes, no values and recreate a table, and then you can implement it using the decision tree, but not directly in the way we had discussed those values. Where is this? What is this F? F is for false. You have to wait? No. You do not, you have to wait, yes, or you do not have to wait. So decision is about waiting or not waiting. So T is about waiting and F is about not waiting. Okay, fine. So now we have to understand this terminology. I told you that there are certain values possible for each attribute. Let us say there is a ith attribute and Vi represents the possible answers. I told you that weight estimate will have 4 possibilities. Yeah. So no means, so if hungry says no, so I'm answering question from Pavan. If you have this, I'm coming back to the slide 11. And if you have hungry as no, so yeah, that is how you have to interpret what it means by true. So somewhere your this hungry thing has true. You are hungry, and you are waiting. Somewhere you are hungry, but you are not waiting. That so it is just not dependent on the hungry attribute. It is the totality of the observation. In totality, certain things happen, and you also observed that you waited, and you also observed that you did not wait. So this F and true in the target weight works with all such values which are forming a particular pattern. It is a kind of pattern that is being observed by this learner. Is it okay? Fine. So now we have to come back and talk about this information content. Then I'll come back to Divya's question. Yeah. So um, here VI are different possible answers, and PVI are the probabilities that answer could be VI. VI here I is the subscript. Then the information content, again this I is small, you can just correct it, of the actual answer is given by, sorry, this I is not small, this is representing the information content here. So this is about I, P, V1, PV2, etc., PVN. So within parentheses, we have taken the probabilities of each possible answer and obtained the information content, right? So the very first sign that you are seeing, apparently similar to minus is only the bullet sign. So please do not get confused. It is just IPV1, comma PV2, comma PVN. That is equal to minus summation PVI log PVI, and it is to the base 2. So the product of the probability with its log value is summed up over all such answers VI which are possible for an attribute corresponding to this set of values. So assume that the training set P, the training set has P positive examples and N negative examples. Then an estimate of the information contained in the correct answer is I P by P plus N, comma N divided by P plus N. Right, so this is the set of probability you have. So if P is the total number of positive examples and N is the total number of negative examples, then P by P plus N is that probability. You know that it is the number of favorable chances divided by total number of chances, right? Or total number of events. So these two are the two probabilities, considering it as a binary classification or binary answered value. Then this comes out to be minus P by P plus N, right? Log P by P plus N. Similarly, the same probability is for the negative class. So N by P plus N log N by P plus N. So summation is taken negative as per the information theory details. You need not go into its derivation, but it so happens that log of the probability, which is actually log of a value between 0 and 1. So log between 0 and 1 is actually coming out to be a negative number, and this minus is to nullify that negative number so that the information content is always positive. You try to compute through your calculator a value where the probability is 0.5, 0.3 and 0.2, let us say. So 0.3 multiplied by log 0.3 plus 0.2 multiplied by log 0.2. Like that you can get the values in negative, and this negative sign gets nullified by the negative sign of log. I is only the information content, right? I is the information content. It is representing, and then it is the log value on the right hand side. It is not the Bayes theorem. It does not have anything to do with the Bayes theorem. It is not calculating any conditional probability. So it is actually the base 2. If you are having in your calculators base 10, you must calculate everything on base 2. So in order to convert your base 10 expressions to base 2, you have to go for another conversion through log of 10 base 2 kind of thing. So try to work out this kind of change. Okay. So I think I left out one question. I'll come back to this again afterwards, because many questions scrolled up after this. So I promised Divya that I'll be coming back to her question. Here leaf nodes are at different levels. So decision can be taken at any level without going through all attributes. So Divya, this is not true, because you have to reach the leaf node right from the root node via all non-leaf nodes on the way. There should be less number of non-leaf nodes, so that less number of tests are necessary, but you must go through all the non-leaf nodes to reach the leaf nodes. Right, so yeah, then Mridula has asked about conditional probability. PVI does not have anything to do with the conditional probability. It is a simple prior probability, and we are not having any kind of Bayes theorem involved in this. This comes out to be a a discussion in the domain of information theory, not in the domain of probability, right? So the the equation about this IPV1 PV2 PVN equals minus summation PVI log 2 PVI. So Biswajit, is this equation clear now, or should I explain? Okay. So is the summation part clear? Okay. Fine. So here summation is taken over all such products where we have a probability of an answer, right? Say for example, uh, I may be hungry or I may not be hungry, or maybe the customers who are coming every day, some of them may be very hungry, some of them may not be. So there is a probability about those answers, and based on those probabilities I am trying to multiply the log of the same probability and add them up together. So this will make one kind of measure to know the information about that attribute. Suppose there is something which you can simply say that that doesn't matter. Nobody has much changes. Nobody has any requirements of such kind of attribute. Can you give me in this context an example of an attribute that doesn't matter much? Will the weight decision matter on your previous day assignments, or will it matter the weight thing, whether you have to wait there or not, will have anything based on your promotion letter? Certain things are not directly associated with this. Whether we go to the restaurant at a particular time, that is very important. If you are reaching there at dinner time, you may have to wait. So this is an important decision, an important attribute. Whether we had reserved the table, yes, this is important. Whether it is a working day or a holiday, again it is important. There could be certain attributes which have no effect on the splitting of the information, right? So that means that particular uh, attribute does not contribute in decision making, right? Okay. So in that context, we are trying to identify the information content hidden in an attribute. Are you getting my idea? Or otherwise, I'll expect you to give me one attribute which has almost zero information content. Can you tell? Which mobile do you have? Maybe which particular company do you have? Will that affect whether you have to wait in the restaurant or not? It doesn't have. Traffic, as you have suggested. Yes, traffic is okay, good. On the road, there could be much traffic, but does it affect your waiting time at the restaurant? Of course, this will have indirect effect. When there is a traffic on road on Saturdays and Sundays, definitely the restaurants are also going to be heavily crowded. That has indirect effect. Yeah, the price, the price will not have that effect on whether you have to wait or not, because definitely only those who can afford the price can come there, right? So you have understood the meaning of the usefulness of a attribute, and this is measurable through a definite measurement which we are giving as entropy. Is it okay? Have you understood the positive and negative samples? Here I am talking about that uh, attribute which can have only binary answers. Say whether I am hungry or not, right? Okay, I will come back to your question about why information content is negative, right? It is not negative, it is actually a negative sign which is included to nullify the effect of that log of a small value. Log of any value between 0 and 1 is actually going to give you a negative value. From there, you will pick up 1 minus sign, get it multiplied to this minus, which is visible here, and then it will nullify that negative effect to give you the positive information content. Okay. So I was trying to answer Navdeep's question about positive and negative samples. It is P for those probabilities for a positive answer for a particular um, attribute. I have taken, say for example, I am hungry or not, right? So another customer who comes tomorrow is hungry or not. So depending upon how many observations you have, you may have 5 samples which you saw were the over of the people when they were hungry, and maybe 7 were not hungry. So the probabilities will be 5 by 12 and 7 by 12. This is only in the case when you have only 2 values available for one particular attribute. If you have 3 values, as you have in weight estimate I showed you, so in weight estimate it is not going to be as simple as P by P plus N or N by N plus P. In these 4 cases, suppose I take here the probability of waiting for more than 60 over a period of time when I have taken, let us say, 100 observations, right? I am taking out of 100 such observations whether the customers of that restaurant had to wait for more than 1 hour, maybe 10 times or maybe 7 times it happened. So I will say out of this 0.7 is the probability when people had to wait for more than 1 hour. So I'm going to make it, yeah, I'm going to make this one with a different color so that you can see what I'm typing. Let it be magenta color, and I'm at slide 11. You can see whether it is visible to you, and I'm looking at the weight estimate attribute, right? It has 4 such possible values, and now I'm trying to figure out how many times customers had to wait for more than 60 minutes. And let us say we had these observations that out of 100 times, they were customers, 7 times they had to wait for um, more than an hour. So 0.07 should be the probability, and they had to wait for about 60 minutes, maybe 25 times they had to wait for 30 to 60 minutes. So this will be 0.25, okay, and for about 10 to 30 it is somewhere around 50, so 0.5, and 10 minutes very less maybe, so it is 0.75, and how much it is left out, somewhere around 24.03, like that. Sorry, this will be 0.25, 0.2403, 24 over, that should be 0.5 plus 0.25, that is 0.75, and I have to make it 1 because these are all the exhaustive events. So 0.07, yeah, 0.18 it should be correct. So this one should be 0.18, and this makes it completely 1 because I am taking all possible exhaustive events. So with these, what are the values? I am having V1 as greater than weight, I mean more than 60 minutes wait. Okay. Likewise, you have V2 as 30 to 60 minutes wait, right? So this way, V1, V2, V3, V4 are representing those 4 answers, and then you can always say P1, P2, P3, P4 are the 4 probabilities. So P1 divided by P1 plus P2 plus P3 plus P4, if that is this much, then you will have several other. I'll show you how. So this much minutes wait, and V2 is V3 is actually the third answer, which says 10 minutes to 30 minutes wait. Okay, so you have understood the meaning of V1, V2, V3, V4. Okay, so V4 is 10 minutes, up to 10 minutes wait. Okay. Now I'm talking about P1. So P1 is actually in this case 0.07. P2 is equal to 0.25, and then P3 is equal to 0.5, right? And it is not necessarily all the attributes met, all the things met. So let us come to P4 equals 0.18. So then you will be actually computing log of P1, which is log of 0.07, right? And then multiply with 0.07. Similarly, you will be computing log of 0.25, okay? And then you will be multiplying with 0.25. Like that, you will be doing to compute the information content associated with this attribute of weight estimate. Is this right? So now here I'm not using the notion of P and N. While here we have P1, P2, P3, P4. N is also nothing but in the binary attribute case, P plus N is actually equal to 1. Isn't it? Is that okay? So then we come to this. Yes, so suppose I'm taking 14 observations. You can always say that if I'm having 14 observations, let us say if P is seen 10 times and N is seen 4 times, then P plus N is 14. So it is only a way to compute the probability. Either you compute a probability or you write it in this form. So basically the probabilities will sum up to 1. Okay. So now we are coming to this computation. When the computation is seen, you can understand what it means. So say for example here, hungry, this fourth attribute. There are some 12 observations starting with x1 to 12, maybe 12 different occasions when this data is collected for 12 different customers, and it is observed whether they had to wait or not. So let us focus on this fourth attribute. You can see when the person was hungry, it is and how many times target weight is true. Can you calculate how many times the value V1 for hungry, V1 is, yes, hungry, right? True. I must write true. And V2 is not hungry, that is false. So can you tell how many times when the person was hungry and the person had to wait? It is 1, 2, then 3, 4, 5 times. 5 times. Shall I mark it? So when this is the first observation, hungry is true and target weight is true. When it is the second observation, x2, then the person is hungry but doesn't have to wait. Third one is anyway false. Fourth is true and the person has to wait. So this is the second occasion when person was hungry and person has to wait. Then comes sixth one. Sixth also is true, both the cases. Eighth is true in both the cases. Okay. Then 10th it is false, and then 12th it is true. So 10th we are not counting in this 5. So 5 times it happened that the person was hungry for V1 equal to T, and the person had to wait for true, right? So similarly for this one, how many times it was true and it did not have to wait, how many times it was false and it had to wait. So this much information you can always find out. Now we are trying to find the information. Let us say certain thing is very simple. Which one are you taking here? For equal 6 times. Let's say for example, which one is the, okay, what will be the information content of this hungry? Can you compute? It is true 7 times, right? So 7 times it is coming here, and 7 5 times it is coming on the no side. So what is P in this case for yes? So P of V1 is actually equal to 7 and not 5. We are not only counting on the true objective, true target. We are counting on how many times it is going to be true. And then P of V2 on no side it is 5. So you have to correct it back that we are only not counting alone those true samples which are amounting to true target weight. We are counting all the trues in Hungary. So the probability will be 7 by 12, right? And its PV2 will be 5 by 12. That is how you have to calculate. So initial answer 7 was right? So this is one example when P was 6 and N was also 6. So it computes to 1 bit. You can always compute it and then you will find that it is 1 bit. 1 bit means that it has only this much information. How much is the information? Can you say that it is good or bad? If certain value is able to split the complete data set in 2 equal parts, is it considered to be good or bad? Yeah, there is one answer. It is good. Why? How can you say that it is good? Suppose it had the particular value says that it is a kind of 1:9 kind of a split. 1:9 is split. So one probability will be 1 by 10, another will be 9 by 10, right? So this is about the information content. Let us look at some more examples here. So we have to see how good your splitting capability of the attribute is. Let the attribute A divide the entire training set into E1, E2, EV, etc., where V is the local number of values A can be tested on. So this is exactly the same formula, but I have now tried to add it to the number of values of I for all such possible answers, right? So we call such kind of information as remainder. Remainder is about computing P of I plus Ni divided by P plus N. These kind of notions will be more clear when we will talk about an example and work out everything. So let us not devote much time to this. Rather, we will come back to this again once you have gained the confidence on the problem solving. So here we will talk about gain, which is actually the total information content minus the remainder of that attribute. So if the remainder is minimum, we will say that this attribute is more informative. So suppose we have these 12 different observations, and if the patterns attribute divides or splits these 12 observations into um, 3 different classes, right? One is based on the none value, another on some value, and one based on full value. Now here there are certain notations which we have used. One is plus, another is minus. This plus and this minus is actually corresponding to the weight attribute, the label of the class or the decision. So let us come back to the example and focus on this none attribute. Okay, I'll show you this one. So where is this pattern? This is here, and I told you that we are focusing on none. So none is the 7th, and none is also 11th, right? So this none has given us one false weight attribute, target weight, and the 11th one also has given us false. So both ways, the none attribute has given us false value of the target weight for X7 and X11 observations. So what are we computing here? X7 and X11, right? False as an attribute of target. So I have given it in a negative class. But there is no such sample contributing from none value to the positive class of target weight. So this sign is basically representing the target, and these are all their values. Okay. So similar thing you can apply on type. So there were 12 examples, 6 belonging to the plus class. Plus is basically representing the weight class, and negative not waiting in the restaurant class. And then if it is the French food or Italian food, and then on that basis, if we are getting certain weight and non-weight kind of attributes, you can see that its splitting ability is very less. It is distributing in both the things. So that means it is not giving us much decision ability. I'll show you another example where you will compute. I'll come back to this later. Okay. So I want to show you first that example where you will be having much more confidence on calculating these probabilities. So yeah, I'm taking this example here. So there are these 14 records, age groups, income, whether a person is a student or not, credit rating, and then whether the person buys the computer. That is to be predicted, whether the person will buy the computer or not. That is what is the target class. So this is again a binary decision problem, binary classification problem, and the patterns are different. Somebody is less than 30, is in high income group, and is not a student, and credit rating is fair. Still the person doesn't buy the computer. That is what is the observation. So there could be one person who is within 30 and has medium income but is not a student, and still the credit rating is fair. Still the person does not buy the computer. So there is certain very, very peculiar thing that makes you predict who will buy the computer. Can you correlate your understanding, your human brain about predicting particular nature of a attribute? Can you say that a particular attribute is of more use, whether it is age or income, or whether the student status of that person? Is this the age? So that means you are always seeing that less than 30 is not buying any computer, but there is one person who is above 40 also not buying a computer. But most of the time it is less than 30, right? So this is one good observation. Whether income scale is a predictive, attribute. What is it that makes us, apply human logic to tell that if this is the income group and this is the age group, definitely the person will buy the computer. Is there any one single attribute which is more informative? Yes, we will have the solution for this. But yeah, of course, with such a small data also, it is difficult for us sometimes to compute the usability of an attribute. Student status sometimes may not be the direct catch, because there are two people who were not the students, still they bought the computer, right? There is one person who is the student, still did not buy the computer. So the chances are less. If the credit rating you see is excellent, sometimes the person did not even buy the computer, sixth record, but seventh record it says yes. So let us say it is a combination that works, right? Somewhere it is a pattern, not just a simple single value which is a decisive factor. Now let us come to this attribute information content, compute this information gain, and construct the decision tree. So you have understood this example. Decisions are binary, yes or no. Then training data is to be seen as example and decision pair, where example has 4 attributes. So R1 and no. R1 is one example which has its own values for 4 such attributes, and no is its decision. Similarly, R3 has a yes decision, R4 has a yes decision, and so on. So we will call all such examples such as R3, R4, R5, R7, R9, R10, 11, 12, and 13 as positive examples. But 1, 2, 6, 8, and 14 are negative examples. 1, 2, so which are the negative examples? 1, 2, 6, 8, and 14. These are the negative examples. This is about the decision class. If the decision class is negative, we call it a negative example. If the decision class is positive, we call it a positive example. So is the given training set sufficient to take any decision? Let us see. Is the generalization capability of the given training data sufficient? Okay, so this also we have to check out. So let us see. So here V1 is yes and V2 is no, right? And positive examples are R3, R4, R5, R7, R9, R10, R11, R12, and 13. These are the negative examples. Total number of examples, it is 14. So just a typo mistake, you can correct it. PV1 is 9 by 14 and PV2 is 5 by 14, right? It is about the target class. So information content is represented by 9 by 14 and 5 by 14. So the total information content in this set is still 0.8. That means this set is not sufficient to give us full information. This set of observation is still lacks much more information which is required because it is not 1, it is just 0.8. That means the kind of split that we have in this table, they are not sufficiently giving us the idea, right? But of course it is good enough to be able to predict certain things. So these were the positive examples in this one. Okay, and when it is low, medium, and high, these are the 3 income group because we are trying to estimate the usefulness of income attribute. So when it is low, for the yes class, it is R5, R7, R9. Shall we go back to the table and see why it is 5, 7, and 9th observation for the income class? So I am cleaning all the annotations here, focusing on income and then focusing on low. So low is R5, R6, R7, and R9. These are the 4 records which are using this low value of income. Of these, R5 is giving us a positive class, R6 is negative, R7 is positive, and R9 is positive. So how many are positive here? There are 3 positive classes and 1 negative class. Okay, so which one is negative? R6 is negative, and R5, R7, and R9, right? So R7, R5, and R9 are positive in this slide 31, and R6 is negative. Is this part clear? This splitting is clear? Okay, so yes and no are representing the target classes, right? And splitting is on the value low of the attribute income. While income has 3 different possible values, V1, V2, V3, where V1 is low, V2 is medium, and V3 is high. Similarly, on medium value, there are 6 samples which are distributing the information. I'm coming back to the table again. Now I'm going to clean all the annotations and show you medium one. So one is this 4th sample, then it is 8th sample, and 10th to 12th and 14th. Okay. So medium is giving us yes, 1 medium. R8 is no, and R14 is no, while all others are yes. So 8 and 14 are no, while 4 are 4, um, R10, 11 and 12 are positive classes. So let us come back to this slide and see. R4, 10, 11 and 12 are giving us the positive class, and R8 and R14 are giving us the negative output class. Output class is whether the person will buy a computer or not. Yes, so we will have to compute the significance of all the attributes. If there are 5 attributes, we will have to compute all the 5 and pick up the attribute which has the maximum information gain. Okay, so we will compute for credit rating, for age group and so on. But here I am showing you as an example the income group, which is computing it like this. So for high also you can observe that it is 3 and 13 and R1 and R2 as the negative class. So what can you observe from this slide? You can see that there is not much splitting capability of the income attribute. It is not saying yes or no. So, you ask a small child whether child wants a chocolate or not. There is always an answer yes. So the decision is so quick. All the time you get the answer without a confusion, right? So see, the attribute should have the proper information. It should have proper splitting ability. So if I now look at this PI and NI, this refers to 3 different indices corresponding to the 3 values of low, medium and high. Okay, so what is going to be P of 1? Let me say, I think I have shown it in some slide here later. Yeah, so in the same example, in the next slide, it is P1 is 3 because there are 3 positive examples, and 1 is an index which is corresponding to V1, which is low. N1 is 1. In the next case, when V2 is medium, then P2 is 4 and N2 is 2. In the third split, it is for high, that is V3. So now I have P3 equals 2 and N3 equals 2. So while the total, this was P is equal to, how much it is? 3, 4, 5, 6, 7, 8, 9, right? It is 9 and N is equal to 5. So before the split, the total positive examples were 9 and 5. So out of 9 positive, we are able to split them 3, 4 and 2. And out of 5 negative examples, we are able to split them in 1, 2, 2. Okay, so what happens next? Now we are computing this remainder. Remainder is P1, right? What is it going to be? P1 plus N1 divided by P plus N. I of P1 divided by P1 plus N1. It is not P plus N. It is P1 plus N1. Within the I, it is P1 plus N1. So what will be P1 plus N1? It is 4, right? That is why I have written here I of 3 by 4. What is this 3 representing? P1. What is 4? It is P1 plus N1. That goes inside the I. And here it is the negative part, 1 by 4. It is because N1 is 1 and P1 plus N1 is 4. Okay. So, and what is this 4? This is P1 plus N1. And what is this 14? This is P plus N. Okay. So have you understood the first term 4 by 14 multiplied by I 3 by 4 comma 1 by 4, right? Then this is only a representation of I. Then I will be computed as per the discussion we had. Minus 3 by 4 log 3 by 4 minus 1 by 4 log 1 by 4, right? So P of I is the positive is the number of samples which are splitting to positive class. Ni is the value of or the number of such samples or observations um, leading to a positive class for ith attribute value. Okay, so try to work it out comfortably and then see the values, and then you can get back to me for more clarity here. It is simple summation over such kind of products. Okay, so remainder means it is the remaining usefulness of that attribute. That means if the total information content sorry, minus the remainder, if that is large, then only we will take that attribute as the root, right? So the root information will be decided on the basis of the attribute which has the least remainder. Okay. Yeah. So I'm taking a small break. After that, I will come back and discuss, um, you know, certain details about the data visualization using Python. So meanwhile, I want you to work out these things for different other attributes as well. So if you want, I'll leave this slide on, and maybe after a 5 minutes break, I can come back and join you back. Okay.